It's nice to be here. Thanks for being here and listening to me. As mentioned, I'm Soroush. I've been working in Toyota Motors Europe for the last year. Before that, I was doing my PhD in Leuven in Belgium, near this beautiful castle. That's why I put it there to advertise it a bit. So today I'm mainly going to talk about the research I've been doing in Leuven. There we were supposed to build a drone actually from scratch that is equipped with a 360-degree camera. This drone is supposed to do a variety of tasks, so traffic monitoring, broadcasting a sport event, doing surveillance, doing inspection in a building, and so on. So there were different teams working on this drone. So some teams, we had a team working on a hardware part of the drone, so they built the 360 camera from scratch. It's made of like 4 cameras back to back, each covering 200 degrees of the scene. So in the end, you have the 360 environment and also the depth there. I play this again. So basically, there were other teams also, like there was a team working on the wireless communication. There was a team working on the low aspects of flying a drone. And we had 2 computer vision teams working also on different tasks, like object detection, localization, obstacle avoidance, and scene understanding. I mainly worked on the localization part and the scene understanding part. So for the localization part, I wouldn't go that much into the details because we basically used some existing computer vision architectures like PoseNet or OrbSlam, and we just extended it to 360-degree cameras. But actually this project allowed us to try to think a bit outside of the box and try to come up with research directions concerning 360-degree inputs. So in order to come up with these research ideas, we first needed to make a couple of observations. So the first observation we had was that actually 360-degree inputs are quite redundant. So if you look at these images there, you see that large part of the environment are like either the sky or the ground or the wall. And actually processing all the pixels in those regions don't add much more details or information for the method to learn anything about the environment. But you actually prefer, also as a human, when you enter a place, you would look at different parts of the place, like this amphitheater, and you would know what's going on there. So you don't have to really look at every corner in this place and process it with your brain to understand what's going on there. So that's basically what we also want to do with this research idea. So as you see, I have a photo that we captured with our toy 360-degree camera. We were using actually this camera mainly for the localization purpose, but as you can see here, again, we have the sailings, we have the wall, we have the path that are basically just uniform areas. So if you give it to a computer vision method, it can process all the pixels there, but it still doesn't add much information regarding what's going on in this scene. But instead, as I said, you prefer to take a look at smaller parts, like there are some bikes there, there is a glass door to the other side, there is a window there, there is a path here, and you more or less know what's going on in this environment. Another observation that we had was that current state-of-the-art architectures in computer vision are mainly based on convolutional neural networks, or CNNs. So one big assumption with CNNs that current architectures take is that they assume that we have a full observability for a task. So basically, if we want to detect an object, you assume that object, like this cute dog, is there and is fully visible for you. So building on this assumption, the CNN would start from the left corner of the image, it processes all the pixels there, and then it can tell you that, yeah, this is a dog. Another big assumption which introduces some bias for the tasks that we are currently solving is that most of the data sets that we are using are taken by human photographers. So as humans, we try to squeeze in as many as objects of interest into the image. We put probably the most important object somehow in the center of the image. And by doing that, we are actually introducing a bias for our training procedure. So the other observation is that if we have an autonomous agent, like a robot, like a little robot, if it has a limited field of view and it can't capture the whole scene, its inputs might not be really consistent with those coming from a common computer vision dataset. So if you train a model on those kind of images, it might not necessarily work in the wild. So for example, at a certain time step, it might be looking at something like this. But if you had a human photographer there, he or she would probably capture something like this, which is quite meaningful to us. But the autonomous agent doesn't necessarily know that it has to look there. And of course, as I said, the autonomous agent can't look at everywhere because it's also quite a lot of parts in the environment are redundant, and also it's quite a time-consuming procedure and it needs a lot of computation. So I don't know if you can guess now what's this research topic about, but I can actually define it in two ways. So the first way is we have a 360 camera. As I said, we have 4 cameras back to back, each one covering a field of view of 200 degrees, so they have overlap. The resolution coming from each one of the camera is 4,000 by 4,000 pixels. So processing all these images would require a lot of computation time and also processing. So instead, we would like to have a kind of method which knows which parts of these images that it's getting as input are the most important parts to process. Or, as it's formalized more in the previous literature, as it's called active visual exploration, you have an AI agent dropped in an environment. It has a limited field of view, so it can't capture the whole scene. It has limited camera movements, so it can turn its head in the environment and look at different areas. But it can't look at everything there, so it has to check the most important parts there. So, and the goal is that it would understand the environment and explore the environment. The evaluation criteria that we use for evaluating if the model is understanding the environment good or not is actually reconstruction. So how well does it manage to reconstruct the environment or classify the environment after seeing some parts of the environment? There's actually a certain pipeline for active visual exploration. So as I said, you start from a random location. So you assume the agent is dropped in that environment. It has a random orientation of its camera. It sees a part of the scene. So we call that small part of the scene as a glimpse. So it takes a glimpse. Then it processes the glimpse with a convolutional neural network to detect the patterns in those glimpses. Then, based on what it has seen at this time step, it tries to update its representation of the environment. So this representation tells the method, summarizes whatever the method knows about the environment. And then, based on this representation, it's supposed to reconstruct the environment, which is doing really bad now because it's just seen some random part of the image in the first step. And again, based on this representation, it has to come up with an idea of what's the best next location to look at. So during this research, we basically worked on every part of this pipeline. So updating the representation, taking the glimpse, how to reconstruct, and how to choose the best next location to attend. But yeah, since I can't talk about all of this, I would try to go for the most interesting part, which is the attention part. So how would you train a model to select the most important part of the environment to look at. Before going to the technical details, I'll try to give you another example to make it sink in your brain. So basically, we have a 360-degree environment. We start from a random location. We take a glimpse. The method has to predict the reconstruction at each time when it sees part of the environment. And at the same time, it has to predict an attention heat map saying what's the best next location to attend. So the area that is lighting up is the area that the method would attend the next step. So as you can see here, it has taken its first glimpse, and the reconstruction is not that good, but it already kind of knows where the horizon lies. And in an exploratory approach, it tries to look further away from the first glimpse and look at the left corner of the image. So it goes to the next glimpse. It sees part of the sky. And as you can see, by just seeing these two glimpses, it already knows that the higher part of this image is probably just the sky. So there's no need to go there and process every pixel there. And there are probably more interesting places to look at. So again, I don't know if you can see it here or not, but here it saw something, but it's not sure what it is. So in the next step, it tries to take a look there, and again, comes up with a better reconstruction, and so on. So as you can see, just by having like, I don't know, 5 fixations on this environment, it more or less knows what's going on there. Well, it's still a simple scene, but that's the main idea for this research. So I would directly go to the first method that we proposed on how to train a model to be able to tell what's the best next location to see in order to explore an environment. So this basically comes from the idea that if you're making a reconstruction of the environment, and if you know what's the worst place that you're making the highest error in that reconstruction, it's probably better to attend that location, because it means that you're probably encoding the least amount of information in that area. So let's say we have a scene, and we have taken some glimpses from the scene. During the training, what happens, as I said, we make a reconstruction of the environment. We have access to the full scene during the training, so we can calculate our loss, our reconstruction loss, and optimize the network so that it will do better in the next turn. And we define another sub-network which tries to predict which is the part in this image that the method is making the highest reconstruction error. And the way that we optimize it is that during the training, we actually have access to the reconstruction loss, so we can optimize the network to predict the area with the highest reconstruction error. And that way, it would choose the next location, and it would attend that. So we published this work on the 360 Perception and Interaction workshop in ICCV 2019. We actually won the Best Paper Award there, and we showed that by looking at 20% of the pixels in an image, you can come up with a very good reconstruction of that image. Still after this work, we got some criticism that, okay, no, you have solved the reconstruction task, but like, what's the application? Like, you can reconstruct an environment very well, but what's the application? Which is actually not really a fair criticism, because this all is a way to show that you can come up with a representation of the environment. So you can plug in any other task on top. And we actually showed that you can also classify the environment like that. But in order to listen to the reviewers that we had, in the next work, we tried to actually tackle a more applicable setting. So instead of doing reconstruction, which only depends on the actual texture of a region or actual colors in that region, we try to tackle a semantic segmentation task. So in computer vision for semantic segmentation, what you have to do is that you classify every pixel in that image. So you would say, I don't know, this pixel belongs to a car, while this pixel belongs to a tree, while this pixel belongs to a pedestrian. And it's actually a much harder task than doing just reconstruction. So the setting would be the same. You take glimpses of the environment, and then you would try to come up with a semantic segmentation for the whole environment. The thing about this research is that we try to go for a highly structured environment, such as like scenes from an autonomous driving dataset, because still we are not able to see everything. So in a highly structured environment, you can still expect the road to always be in front. You can expect cars to be there. You can expect pedestrians, but it doesn't occur that all of a sudden an object would appear at the top of the image in like more unstructured environments. And at this work, we also proposed the second way that a method would learn what would be the best next location to attend. So the idea here was that the best next location to attend is the area that you are most uncertain about. So again, as humans, if you enter a place, you would probably take a look at areas that you're not very certain what's going on there. So we injected this measure of uncertainty into our method using our loss function. So at each step, the method has to predict a segmentation map for the environment and also a certainty map, which tells that for each one of the pixels that it has predicted a segmentation, how certain is it about its predictions. So basically the areas that are lighting up are the areas that it's quite certain about. And in these images, they belong to either the visited glimpses or just in front of the car, that the method probably knows it's just a road. And how do we train this measure of uncertainty? We predict an extra channel called our certainty map. We define a variable who has a direct reverse relationship with our certainty map. We call it our uncertainty map. And during training, we have access to the ground truth segmentation map of the environment. We can calculate our predictions error. And then our loss function would look like this. So the error multiplied by the certainty map added to the uncertainty map. So it might not be really clear what's happening here, but if you take a closer look at it, the method has to minimize the loss function there. So basically, for the areas that we have a high error, it has to assign a low certainty to that region. And consequently, it would assign a high uncertainty to that region. So basically, the method still learns for the areas that it's making high segmentation errors, it would learn to assign low certainty to those areas. So one aspect of this work which was really important, apart from like proposing a new attention mechanism and like changing the application to semantic segmentation, was that we compared our method with another method that you can see in this table that has access to the full image. But instead of processing it in full resolution, it would resize it to a number of pixels equal to the number of pixels that we would see in a glimpses. So it has to still scale it down quite a lot. And we compared our method, which has access to full resolution glimpses, to this method, which has to resize the image to a number of pixels equal to the total number of pixels in the glimpses. And as you can see in the table, we do comparable with this method, although we are achieving a lower average, but it's mainly because there are a lot of areas that you can't see in the environment. But the main thing was that we noticed that for certain object categories that are quite small, like humans, what happens that if you resize the image to a much smaller image, what happens is that those details are removed from the image. So the method that has access to the full image can't really like predict existence of pedestrians there, while our method can take a look at different spots in full resolution and then also detect pedestrians also. So basically what we proposed in this work was a hybrid approach that uses both the downscaled image, if you have access to the full environment, to just see what's going on in general in the environment, and then use our method to look at different parts of this image in full resolution to capture the details there. So I'm running a bit out of time. So this brings us to the third attention mechanism that we propose. There, instead of relying on a segmentation map or a reconstruction map to guide us or like to train our network, we try to look at internal activations of our network and use those activations as the attention mechanism. So basically, we looked at self-attention layers in our network. So self-attention layers are basically consist of certain channels, as you can see there, it's called raw channels, that detect patterns in the image, and one extra channel, which is called the attention map, which weights those raw channels there. So basically, this attention map is giving importance to different parts of the image according to the final task in each layer. So if like an area lights up, it means that for the final task, that area is more important compared to the other areas. So for this attention mechanism, what we basically did was that after each time that we did a reconstruction, we looked at the internal activations of our network, or the self-attention layer on the last layer of our network. And if there was an area that was lighting up, but we hadn't visited it before, it meant that it has a like important influence for the final task. So for the next step, we would try to attend that area, and so on. So basically, what was important about this work was that you could train a network directly for a classification task or a regression task like camera pose estimation without a need for a dense prediction task like segmentation or reconstruction to guide your attention mechanism. So up to here, I mainly talked about the attention mechanisms that we introduced there, but it's also nice to talk a bit about the representation. Because up to a year ago, when we were working in our last paper, we were still using convolutional neural networks, or CNNs as you call it, to encode our glimpses. So the problem here is that convolutional neural networks normally detect patterns by first looking at local regions in the environment. They detect local patterns there, and then using the pooling layers, they try to come up with more general patterns or more abstract patterns or bigger patterns in the image. So if you have an image like this, it would start, as I said, from the left corner of the image. It would look for the local patterns, and then pooling layers would downsample these detected patterns, so it could look at the bigger image there. But the problem for us was that the glimpses that we are taking are already really small, so we have a limited field of view there. So there might not be really big patterns there that you want to detect. And by using pooling layers and by downsampling these glimpses, you even lose more information, which are actually quite important to us because we can't access the full image. We just need basically all the information that we are taking from the glimpses. So it's actually a not ideal backbone for our network. On the other hand, in the last 2 years, there is an architecture introduced called vision transformers that are more or less now replacing the CNN backbones, and they're showing a lot of improvements over CNNs. So what they do is that they divide an image into patches, but process each patch in a constant resolution. So there's no downsampling happening there. So your patch would always have the same resolution throughout the network. And detecting patterns happens first with the positional embedding of each patch. So basically, the method knows that this patch is coming from here, and this patch is coming from here, and this patch is coming from here. And then also using multi-head self-attention layers that are actually now quite trending in the computer vision community. So basically, in the next work, which is gonna be published in VACV 2023, we changed our CNN backbone with a vision transformer backbone. And what happened was that we saw that now using even smaller glimpses, you can come up with much better reconstructions that are sometimes even hard to see by humans. So for example, if you look at these patches from this image and you try to reconstruct it in your mind, you probably can't do it as good as this. So actually, apart from the attention mechanisms that we proposed previously, we also changed the backbone for our network, and we showed that by doing that, you can get much better and impressive results there. So, yeah, I'm almost out of time. The research that we have done is still not complete, so there are a lot of problems with it, probably. So one problem is that if you have a fully accessible input, so if you don't take this assumption that you have an agent with a limited field of view that can't look at everything, if you take out this assumption and you assume that you have an input which is fully accessible and it's not very large, so it's small, our method works still slower than just processing everything with a CNN. Why is that the case? Because our method is still sequential. So you have to take a glimpse of the environment, do some processing, then choose the next location, repeat the same processing for that, and so on. So basically, in terms of computation time, on some applications that you have the fully accessible input that are not very large, our method still works slower than the actual normal CNNs. Another problem is that our methods are really memory hungry. So basically using a vision transformer these days, I don't know if you have worked with them or not, but nowadays they are training vision transformers on like 10 GPUs at the same time for a week. And so yeah, it's not really efficient to do it that way. And I think an extra line of research would be really interesting is to apply the same on videos. So basically now we are working on static images. So we are exploring a static environment and telling what's happening there. But it would be much nicer if you could like take a glimpse from each frame in a video, and basically by doing that, instead of processing every frame in that video with all the pixels, you process the small glimpse in each frame and know what's happening in that video. So that concludes my discussion for today. Thank you for listening to me.